All right, hello and welcome back to Revolvolus. It's my favorite time of the week, which means that, we get to go through another section of content. And today we got a really interesting topic. We're sort of drifting away from discussing forces. The last two lessons were about different types of forces. We explored, gravitational force, normal force, frictional force, all sorts of stuff, tension. Uh, those ideas are still going to apply in today's lesson, but now we're going to focus a little bit more on something not I wouldn't say abstract, but not a specific type of force. Well, it's still forces. You'll see. Let's just introduce what is today's topic. Today we are talking about gravitation. And you might be like, oh, gravitation, gravity. So maybe that's giving you some insight that we will be talking a lot about gravity, and the main force we will be considering is the force due to gravity. But we've already kind of learned about force due to gravity, F sub g equals mg, and you're like, well, I already know what that is. Not yet. When I introduced Fg, I remember saying that this force is for objects in relation to Earth. For an object on Earth or close to Earth, then the equation is Fg equals mg. Today, we're going to answer the question, well, what happens when we're not on Earth? So let's figure it out. Let's just jump into today's unit on gravitation, lesson 6. Here we go. So, as always, we will start with some definitions and, get the main stuff out of the way. So, we see Newton again, like, man, this guy has done a lot of stuff. And it's true. He's done so much stuff, not just in the world of physics, but also in the world of calculus and math and, all of these different fields. So, when we think of Newton, we think, like, man, that guy was smart. But nah, he was like a genius coming up with all of this stuff. Anyways, I digress. Newton's universal law of gravitation. Keyword is universe, and I highlighted it in the definition, but let's read the definition, which is just paraphrasing it. But essentially what he said is that every particle attracts every other particle in the universe with a force. So this means if we have two particles, two objects, they can just be any random objects in the universe, not necessarily on Earth, they're going to attract each other, and there's going to be a force between them. And Newton tells us that this force, F, equals capital G times mass of the first object times the mass of the second object divided by r squared. We'll look at what this r squared term is in just a moment, and we'll look at what this capital G term is in a moment as well. But we should be seeing that, okay, the force is directly related to the product of the masses of the objects. Just something to keep in the back of our head. So the first bullet point here, the force is inversely proportional to the square of the distance of separation. So r is a distance quantity that measures the distance between the two objects we're looking at. We're looking at two objects because, m1 and m2. It's the force between two objects. So r is the distance that separates them. And usually, when we look at objects that have that are very large, we compare the distances from the center of mass of the two objects. Okay, so that just comes from the formula, right? We have an f here, and then r squared in the denominator, so it's inversely proportional to the square of the distance. That makes sense? And just like I pointed out previously, the force is directly proportional to the product of the masses of the two objects. That just comes from m1 times m2 in the numerator. And going back to Newton's third law, the forces are equal and opposite. So like we said, we had two objects, and there's a force between them, so there should be an opposite force. And that's shown in this diagram right here. I don't know what I'm trying to draw here. I'm trying to draw a star, but that does not look like a star. There, better. Okay, so this is one object, this is another, and then the arrows show the force between them using this equation up here. And notice how they're they are equal in size, but they're pointing in opposite direction. They point towards each other. So the forces don't point away from each other. So these red arrows would be incorrect because the forces, they attract. That's a good way of thinking of it. Attract each other instead of like repel. And then we can see here that the distance r is measured from the center of masses of these two objects. We'll just assume a universal like spread of the mass within that object. Okay, so that's the formula. We know m1, we know m2, we know r squared. Just need to figure out what this g term is. So let's take a look at it. First, let's just recall the r from the equation. I'm just going to rewrite the equation so we have it for reference. F equals g times m1 times m2 all over r squared. So the r in the formula might be confused for radius. But like I said, in this case, r is defined to be the distance between the center of masses of the two objects. So I said it might be confused for radius because this equation is used for any two objects in the universe, like I said. So when we consider objects that aren't on Earth in the universe, the only things we really have to consider are like other planets and other stars and stuff like that, right? We don't really know what kind of objects are on other, like elsewhere in the universe. So since that's kind of all that we are familiar with, many of the problems require us to use these planets or stars or stuff like that. And for most of them, we assume those shapes to be circular, right? We just say a planet is spherical or circular. So in those instances, it can be confusing that we have an r squared term. Sometimes students think that we take the radius of the planet or the star that we're working with, when in reality, r squared is the distance between the two objects we're working with. So that's just a little point of clarification and something for you to keep in the back of your mind. Okay, now let's figure out what this g term is. G, capital G, is the gravitational constant, and it acts as a proportionality factor. So it's just a constant number, and in this case, well, in all cases, capital G is equal to 6.673 times 10 to the negative 11 newtons times meters squared divided by kilograms squared. And if you do the unit calculation, Newton times meter squared divided by kilogram squared, and then you multiply that by meters times meter over, kilogram times kilogram over meter squared, you'll see that those cancel, and then we'll just be left with newtons, which is why force should be in newtons. So this is our gravitational constant. This is always going to be the number we use for capital G. And capital G is different from lowercase g, and we will explore that in just a moment. But first, I'm just going to clarify a couple of things. Actually, these are just things we should be familiar with, because in this unit, we're going to be talking a lot about planets and stars and stuff like that. So if we're trying to find the velocity of a star or something in orbit around like a sun or a planet, we can think about that as, well, we know velocity is equal to like distance divided by time, like displacement divided by time, something like that. So in this case, the displacement could be measured by like the circumference of orbit. That's the distance that a planet travels around a star, perhaps. You take the circumference of the orbit and you divide it by the time it takes to make the orbit. This should say to make an orbit. Right? So that's just like a distance divided by time calculation. And when we do that, we see that circumference is equal to 2 pi r for circles, and time is capital T. And capital T is the variable we use for period. So period it's defined to be the time it takes for something to make an orbit. That's just simply the definition. So that's what capital T is. And this is going to be a very helpful formula down the road. So V equals 2 pi r over capital T. Cool. Let's move onwards. So now we'll ask the question, like, why is lowercase g 9.80 meters per second squared? Like, how do we get that? So you can read this thing on the left here, and I'm just going to use that with the explanation. But basically what we know is that if we have an object of mass m and it's close to Earth, our formula for the force of gravity is equal to mg, right? This works when your object is close to Earth. However, we know that Fg is also equal to capital G m1 times m2 over r squared. And that it doesn't matter where we are in the universe, that formula will always hold. So it just happens when we're close to Earth, we get this equation, or we get two equations, right? So we can set these equations equal to each other, and we get mg equals g m1, m2. Actually, I'm not going to use m1 and m2 over r squared. So let's just zoom into this. So we're looking at two objects, right? We have an object of mass m, which we're given, and the other object in this case is the Earth, right? That those two objects cause those equal and opposite forces, and in this case, the equal and opposite force is Fg. So I'll just say m sub o is the object, and m sub e is the Earth. So m sub o is mass of the object, m sub e is mass of the Earth. On the left-hand side, we have mg, so we should probably give a subscript of which quantity we're looking at. And it might be a little confusing, like do we need to put m sub o or m sub e? And a really good way of thinking about this is if we just ignore the entire right-hand side and we were just going to calculate f sub g normally, we would just put the mass of the object in. M times g would be mass of the object times g. We don't put the mass of the Earth, right? That would be ridiculous, because then no matter what the mass of the object is, f sub g will always be mass of the Earth times gravity. So it doesn't make sense to put m sub e on the left-hand side. So it is, in fact, m sub o. And we're trying to solve for lowercase g here. And we can see that the m sub o's actually cancel. And we're left with, whoops, that is not right. We're left with g is equal to capital G times m sub e over r squared. And so we know that, like, capital G is equal to 6.67 times 10 to the negative 11. The mass of the Earth, we can search up an encyclopedia, and that's 5.98 times 10 to the 24. And then r, now this is a interesting point right here. For r, we use the radius of the Earth. And you're like, wait, hold on a second. You just told me a minute ago not to take the radius of the object. What is going on here? And you're totally right. The reason why we take the radius of the Earth here to be r, I'm just going to write it down for now. The reason why we do this is because we're working with an object that's close to Earth. So that could mean that it's on Earth's ground, or maybe it's like on a table on Earth. So if we were to actually calculate the distance from the center of Earth to the center of mass of that object, that number, it'll be so close to the radius of the Earth, because its distance to Earth is just so tiny in comparison to the actual radius of the Earth. So the radius of the Earth gives us a nice approximation of that distance, since the object is so close to Earth. Hopefully that makes sense. And if we do this huge calculation here, we'll get that lowercase g equals 9.80 meters per second squared. So we can do a very similar thing here. If we wanted to find lowercase g for another planet, or maybe the moon or something, it's a very similar process. This term stays the same because it's a constant, but what we can do is if I wanted to find lowercase g for Jupiter, I would put the mass of Jupiter instead of this term, and then in the denominator, I forgot to put the squared there, In the denominator, I would put the radius of Jupiter squared. And that would give you your lowercase g value there, whatever that is. Is it like 24? I don't remember. It's been a while. So yeah, that explains to us why lowercase g is 9.8. For the past few weeks, it's kind of been a mystery, like, yeah, it's 9.8, let's just roll with it, makes sense. Now we kind of see why that's true. Awesome. So we're just going to jump into questions. There wasn't too much content to cover. And so, yeah, so we have a few questions today, and let's just do it. So our first question is, we have an object with weight W, so keyword is weight, and it's on the surface of a planet of radius r, so it's just a planet. We're asked to find what the gravitational force of the object will be after it has been moved to a distance of 4r from the center of the planet. Okay, so let's take a peek at what we're doing here. For these, it might be helpful to draw pictures, sometimes not. So let's just draw a picture. We have a nice little planet here, and I'll actually make two of them since we have two cases. And we have an object that's on the planet, right? And then, in the second case, the object is moved away such that now it is 4r away, when originally it was just a distance r away from the planet. And it's saying there's some fg old here, and then fg new here. Okay. So, let's see. We're given that the object has a weight w when it's on the planet. So, what is weight? Well, by our previous weeks of information, and sort of by definition, weight is given by f sub g. So even though now we have two equations for f sub g, we have mg and g, m1, m2 for r squared, the properties about f sub g still hold. Weight of an object is still f sub g. Except now, since we're not working with Earth, we're working with some other planet, we have to use the other equation, g m1 m2 over r squared. That is the weight of the object. So, in fact, I'm just going to change the denominator here to a capital R, because that's the radius that we're given. So now we want to see what happens when the distance has become 4r. I'm just going to zoom in here, and let's just change these subscripts. So one I'll make m sub o for mass of the object, the other one will be m sub p for mass of the planet. So when r equals 4r, that's a little bit confusing here, but this is just saying when our new distance of separation is 4 times the old one, maybe I'll put some subscripts here. R sub 0, r naught is the original distance of separation, and then we'll have this new r equals 4r naught. Then we get f sub g equals still g m0 mp over r squared, but now we can make this substitution in, and we get that is equal to g m0 mp over 4r naught squared. Just do a little bit of simplification. This is equal to 16r naught squared in the denominator. So this is the new gravitational force. That's the old gravitational force, or rather the weight of it. So what we can do is, if we go back to here, we can just break this apart a little bit. m0 mp over r squared, or r naught squared, And we see that this is the same as that. So what are these two? They are equal to Fg, or the weight. So we can make that substitution and say this is equal to 116 times Fg old, and that we used was the weight of the object. So it's equal to 1/16 W. And that is our answer there. So what does this tell us? This tells us if we have an object, if we have two objects, and we increase their distance of separation, the magnitude of the force experienced decreases. In this case, it decreases by the squared term of the amount that we separated it. And quickly, just for practice sake, I'm going to draw the force vectors. So in this case, the force points downwards from the object and upwards from the center of the planet. So this one should make sense, right? You just think about it Fg normally. Fg always pointed down towards the center of the Earth or the other planet. Here we're just saying that, okay, there's an equal and opposite force now. And in our second case, it's a similar thing. Fg points down, and here it points upwards, except for the sake of what we just did, I'm going to make these vectors smaller just to show that the magnitude of the force is, smaller. And this should really make sense, right? Because you might be thinking like, if every single pair of objects in the universe experiences a force, between them, then why aren't we considering all of these forces when we solve physics problems? Why are we just neglecting them? And now you can start to understand why, right? We solve physics problems, many of them are on Earth, right? So we have two objects, and first of all of the other stars and planets, they are light years away. So if you put light years into this denominator, and we square light years, which is an insanely large distance, the amount of force is going to be negligible. It's literally zero, maybe 10 to the minus. I can't even fathom how small that exponent is. Minus 100,000, 10,000. I can't even predict that. But you can see that making that denominator super duper large is going to make the force extremely small. And that's the case with other objects, even on Earth, too. Usually, the distances are just, the term goes to zero very quickly, especially because this g term is very, very small. It's raised to the -11 power. So it's a very, very, very small factor being multiplied by masses, which can be very large, but then the denominator is radius squared, which can, make the term go to zero. So hopefully that clears up a little bit of confusion. But now, hopefully you can see a connection between distance between objects and how that affects the force between them. All right, let's move on to the next question. And you can read it. I'm quickly going to take some hydration. Okay, so hopefully you've had time to read it. And this question is asking a somewhat similar question to before. We have, in this case, a satellite moving in circular orbit around the planet. And again, we increase the distance between the two objects, except now instead of looking at the gravitational force, we're looking at the velocity. So, like I said earlier, it helps to draw a picture of what's going on. So, we have some sort of star here, and I'm happy that we're working with stars because I can actually draw circles. And then what I'll do is make a dotted line, and that'll describe that's like the orbit of the satellite. So I can draw like a little satellite here. It'll be a little triangle thingy. Okay, so it's moving in circular orbit, so let's just draw a velocity vector for it. Let's just say it's moving this way with speed v naught, and it's at a distance r from the center of the planet. So this should go towards the center. And then we want to consider what happens when it's at a distance 2r. So let's just draw that down here. Same planet, do my dotted line thingy. One of those, try to make them concentric. And then we have the satellite here. Color that in. And now the distance, whoops, I don't want it to be red. And now the distance is 2r. So what happens to the velocity? V equals question mark. Okay, well, let's take a look here. I'm actually just going to erase the radius that we just made, and I'll just redraw it here. So that's r. Okay, so we have the satellite and we have the planet. So two objects, so that means there's the force of gravity between them. And as we've seen, they point towards each other. So Fg and Fg. And those are the only forces we see. There's no friction, no normal force, nothing like that. And you're like, okay, well, I kind of seen this before. Something moving in a circle with a force pointing inwards should be reminiscent of something we've learned previously. You should be thinking centripetal motion, centripetal forces, stuff like that. So let's do it. Let's sum the forces. I'm going to move this drawing just so we have some room to work with. So let's sum the forces. The sum of the forces centripetally equals the mass times the centripetal acceleration of the system. And, well, we only have one force present, and it is causing the centripetal motion because it's pointing inwards to the circle. So that force is Fg. That equals MAC. Okay. Well, what do we know about Fg? Normally it's mg, but since we're not working with Earth anymore, we have to use our other equation, g m1 m2 over r squared. That equals MAC. Okay, at this point we probably want to figure out what are all of these m terms. What is m1, what's m2, what's the m on the right hand side. So let's specify it. So let's just say the left hand side is g ms, I'll say is the mass of the satellite, times mp is the mass of the planet. And then on the right hand side we have an AC and we have an m. We need to figure out what the m term is. And once again, you should think like on Earth. We have an object that has some sort of acceleration, centripetal acceleration on Earth. We never put the mass of the Earth on the right-hand side, so it would be illogical to put the mass of the planet on the right-hand side. And since we're looking like the free body diagram of the satellite has the Fg, which is causing the centripetal motion, we should have that's the mass of the object we're concerned about. So hopefully that makes sense. Okay, and now you might be like, what in the world is going on? We kind of need velocity, right? That's what we're most concerned about, and that's a quantity we're given in the old situation. So hopefully you remember that a sub c has a formula, and that a sub c is equal to v squared over r. So we can make that substitution. V squared, let me do my curly v. Yeah, I guess I should specify that. This symbol here is a lowercase v. It's a curly v that I use a lot. But I do interchange between this v and that So those are the same things, kind of just depends on the context, what I'm doing. So I just wanted to make that distinction so we were clear about what I was writing. My handwriting can be strange. Okay, anyways, moving onwards. Let's solve for v because that's kind of what we're curious about. So we can multiply both sides by r over m sub s to isolate the v. So we get v squared equals g times ms mp over r squared times r over ms. So I really wanted to get rid of this term, so I multiply both sides by r over ms. Okay, and now we can do some canceling, right? This r cancels with one of these r's. This ms cancels with that ms. And we get v squared equals g times mp over r. And really, v is equal to g mp over r square root of that quantity. So that's the initial velocity of the system. That's the initial velocity of the satellite. So now we need to go over here. What happens when the radius, the distance between the two objects, is doubled? Well, we just developed an equation for velocity. We said that it's equal to square root of g times mp over r. But now the radius isn't what it used to be. In fact, let's just go here and let's just say that this is r naught, our original radius. So now radius is equal to 2r naught. Right? We just doubled the distance between the satellite and the object. So let's just plug it in and see what happens. V is equal to square root of g times m sub p divided by 2r naught. So that's our original velocity, that's our current velocity, and we can see from the answer choices they kind of want it in terms of the original velocity. So that comes back to this equation. So we might want to make it reminiscent of this equation. And what we can do is we can say that this is equal to the square root of 1 over 2 times g times mp over r naught. And by properties of square roots, we can break this apart. G times mp over r naught. And now you see that that is the original velocity that we were working with. So this comes to 1 over the square root of 2. That's just simplifying this here. This is equal to the square root of 1 divided by the square root of 2. Square root of 1 is 1. So that times v naught. So that's just equal to v naught over square root of 2. We can rationalize the denominator if we feel like it, but what we'll realize is that this is answer choice B. Okay? So now, let's take a moment to think, what did we learn about this? Last time we learned when we increase the distance between the two objects, the gravitational force decreases. Now we learned that when we increase the distance between the two objects, the velocity also decreases. In this case, we're dividing it by a term that's greater than 1. So how do we know how much to divide it by? We divide it by the square root of the term of the multiplicative term. So what does that mean? We start from radius r and we went to radius 2r, so we multiplied by 2. So that means our velocity divides by the square root of the multiplicative term, which is 2. So we get v naught divided by square root of 2. If instead, like in the previous example, if I went from r to 4r, then our answer would be v naught divided by the square root of 4, or v naught divided by 2, the velocity would halve. So, yeah, now we kind of have some characteristics of what happens when radius increases. Cool. Let's move on to the next question. So now we have two stars, identical stars, and they're at a fixed distance, d apart. They revolve in a circle about their mutual center of mass, which is shown in the diagram. The stars have mass m, speed v, capital G is just what we're used to, 6.67 times 10 to the negative 11. And now we need some sort of relationship between a bunch of these quantities. And we can see that all of the answer choices are concerned about v squared. So if we can solve for v squared, we're golden. So we should be thinking that we have two stars, and that's it. They're going in a circle, which will be helpful in just a moment. The first thing we think is two stars, force of gravity between them, using the formula we just learned. So in this case, the forces point inwards towards each other, and we were given that they're a fixed distance d apart at all times. So even as they revolve and one star is here, the other one will be directly opposite of each other. So that's just saying that they will have like this directly opposite relationship. It's not like one star will be up here while the other star will be like somewhere down here. That just won't happen because then their distance isn't d apart. Okay, so we have these forces. Actually, let's just go back to what I was saying. So we have, at some other point in time, the stars are here. And in this picture, well, they still have forces, right? There's still two objects. So they have that gravitational force between them. So they point like that. And now you can start to see that, okay, these are all FGs. FG always points to the center of the circle. And now hopefully the alarms are starting to ring in your head and you're thinking that I know how to do this. This is centripetal motion. And it is. But let's not get ahead of ourselves just yet. First, let's figure out what this FG is. We said that we have to use the equation that we just learned because it's not Earth anymore. So, what are the quantities? G, we know what it is. That's constant. M1 and M2. That relates to the two stars, right? But they have the same mass, which we're given to be capital M. So this is equal to G times M1, M2. By the way, this is R squared in the denominator. So now the question is, what is R? Should be careful here. R is the distance between the center of masses of the two objects. So one center of mass is here, the other center of mass is there. The distance between them is given by D. So we're saying F sub G is equal to G times, I need to get rid of these subscripts now, M times M over D squared. Okay. So now let's just take a look at one star. I'll copy this so that way we can see it. Okay, so let's just zoom in here. So let's take a look at one star. We have this like circular orbit, that's just part of it, and we have the star at some point, and the force is pointing inwards. And just as we were getting excited about earlier, this should be priming you to think centripetal motion. We have a force pointing inwards towards the center of the circle, so that's exactly what we'll do. Fc equals MAC. We only have one force that's providing a centripetal force. In fact, we only have one force to worry about, so we say Fg equals MAC. And you're like, why are we doing this? Well, because we know we can get velocity from A sub c, because A sub c equals v squared over r, and we need these velocities from the answer choices. So let's do that substitution, but first we can make a substitution on the left-hand side. F sub g, we just figured out what that is. So let's make that substitution, g times m over d squared. That is equal to MAC. So I made the M capital M because M relates to the mass of the object of which the centripetal force is being applied on, which is just a star, and the mass of that star is capital M. And I forgot that the main point of this was to make a substitution for A sub c, which is v squared over r, just by formula. So now, you're like, wait a second, we're almost there, right? We have that v squared and we can solve for it, but what's this r term? We don't really have an r. We have a d, but not an r. So now we need to figure out, what is this r? What is r? You might be tempted to think that it's d, because over here, we said r is d. Unfortunately, that's not the case. You're like, wait, what in the world? R was just d and now it's not d. And the reason is, well, we have to be very careful with definitions. So let's just make a couple of points here. I'll write it out. In gravitation, where f sub g equals g m1 m2 over r squared, the r is the distance between the center of masses, I'll just abbreviate like that, of the two objects. However, in centripetal motion, hopefully I spelled that right, motion, where AC equals v squared over r, the r is the radius of the circular path. So, what does that mean in our example? Well, this is our circular path. We know the distance from here to here is d, so that's the diameter of the circular path. So the radius is half of it. So in this case, on the right-hand side, r is d over 2. So let's put that all together. We have g times m over d squared equals m times v squared over d over 2 squared. So let's just simplify this. We get g times m squared over d squared on the left-hand side. On the right-hand side, we have m v squared over d squared over 4. Sorry, these are equal to each other. We can multiply by d squared over 4 over m on both sides. So we have v squared equals gm squared over d squared times d squared over 4 over m. And we see some cancellations. That cancels with that. That cancels with that. This 4 can go to the denominator here. And we get v squared equals gm over 4. Did I do that right? I don't think I did this right. I didn't do this correctly. Okay. The reason is that this is an r on the denominator. So this is something you want to be careful of as well. In this gravitational, the r is squared in the denominator. Centripetal motion, it's a normal r. So let's just fix this. This is d over 2. This is d over 2 here. And then what happens is, I'll just rewrite all of this so we're not confused. This is g times m squared over d squared times d over 2 over m. And then we see that, okay, stuff still does cancel. 1m cancels up here. 1d cancels down here. The 2 we can move to the denominator. And then this is g times m over 2d. And if we look at our answers, that is answer choice B. So yeah, Sorry, small mistake there, but it's a good learning lesson, something that we have to be careful of in the future. Be wary of squared terms in the denominator and non-squared terms in the denominator. Something to look out for. Okay, we'll move on to this question now. So we have a spacecraft orbiting a sun, and the first part of this question is just asking us to draw the velocity, acceleration, and force vectors. So this is basically a circular motion question. We saw this last week. And, should remember that the velocity points tangentially to the path of travel. And then we should also remember that the force and acceleration both point inwards. So this we'll call the acceleration, and this we'll say is the force. Let's specify what force it is, because now we've kind of learned about it. We have two objects, a spacecraft and the sun, so F sub g is the force pointing inwards. Okay, this is part B. We have to derive an equation for the orbital period capital T, so there's that variable again, of the spacecraft in terms of m sub s, so mass of the spacecraft, capital M, mass of the sun, and r. So we'll get started with that in just a moment. I've been talking a lot. Okay. So, going back to our drawing up here, we sort of kind of created a free body diagram. We drew the forces present. Note that there's also a force coming from the sun, but we're not going to worry about that for now. We have a free body diagram for the spacecraft. So I'll just quickly sketch it here. It's something like this. That's the spacecraft and FG. We have a circular motion. We have a force pointing inwards. We should be thinking, let's sum the forces centripetally. So let's do it. F sub c equals MAC. The force is F sub g. That equals MAC. Again, we're not working with the Earth anymore. In fact, we're working with the sun, so we have to use our new equation, g times m1 m2 over r squared. We're given that the mass m1 could be the mass of the spacecraft, that's m sub s. m2 will be the mass of the sun, so that's capital M, and radius is capital R. So let's just use the notation that we're given, capital M over r squared equals m, and in this case it's the mass of the satellite, just for reasons specified earlier on today. Mass times a sub c, we make that substitution, v squared over r, and in this case r is the radius of the circular path, and we make that substitution because we're solving for orbital period. So why did we do this? We're solving for period. I don't see any capital T anywhere. Well, if we recall from very early on in this PowerPoint, I made a brief point about how velocity is equal to circumference divided by time of orbit. And I did some explanation and said that this equation comes out to 2 pi r divided by something called capital T. That was at the start of the presentation. So that's why we did all of this expansion here. We want T, which relies on a 2 pi term, which is constant, an r term, which we kind of have, and a v term. So that's what we're going to solve for here, and then we can sort of plug it into here. In fact, let's just plug in this equation into v here, so that way we can solve for t. So let's do that. This is equal to g times ms times capital M over r squared times ms, which is equal to ms over r, so I'm just grouping these two terms together, times v squared, and v squared is equal to 2 pi capital R over t squared. Cool. So we have this huge equality. Now we just need to solve for t. So this gives us g times ms m over r squared, which is equal to ms times 2 pi r quantity squared over t squared. I'm just going to hope that I don't make any algebra mistakes like I did last time. G times ms times m over r squared is equal to ms times 4 pi squared r squared, all of this over t squared. Am I forgetting a term? Yeah, I forgot this r term. See, already made a mistake. Okay, so now we can say that if we multiply both sides by t squared, we get t squared times g times ms times m over r squared equals ms times 4 pi squared r squared, all of this over r. I could be canceling some terms, but I'll just save that for the end, because that's when the fun happens. We'll multiply both sides by the reciprocal of that term. So we get t squared equals ms times 4 pi squared r squared, all over r times r squared, all over g times ms times m. And now we get to do the fun part, cancellations. ms cancels with ms. One of these r's cancels with one of the r's up here, and unfortunately that's it. So not too much cancellation, but we get t squared equals 4 pi squared r cubed over g times m. And we're solving for the period, so we take the square root of 4 pi squared times r cubed over g times m. And that is our answer. And in fact, what we just did is we sort of derived Kepler's third law. If you're familiar with Kepler, this equation is very similar to something that he concluded. And well, what is this telling us? Rather, to make some conclusions off of it, we're going to look at this equation here. And the main conclusion that Kepler gathered is that the square of the period, which means the time it takes to make an orbit, that quantity squared, is proportional to the cube of the radius of the orbit. That was a huge discovery, and it's something that's really interesting to think about. But of course, the period also depends on these terms here, so I think it's very interesting how the period depends on the mass of the object that you're orbiting. Keep in mind, this is a capital M, so from the problem, capital M was the mass of the sun. Notice how there's no m sub s in our equation, so it doesn't really matter how massive the spacecraft is, the period will be the same, so long as it orbits at the same distance. So that means if I go back here, and if this spacecraft, the distance here to here is r, if spacecraft 1 is equal to 10 kilograms, not only have you done what is nearly impossible and created a spacecraft that's 10 kilograms, I'm just kidding, like hypothetically, but if you have a spacecraft 2 that's 1,000 kilograms, as long as they both orbit at a distance r, their period is the same. However, if instead of the sun, we made it Earth, then this term in the denominator would change. It would become a much smaller number, and that would make the period go up. So those are just some things to think about. Think about how things change when we alter some quantities that we can alter. We can't change this 4 pi squared over g term, because those are all constants. But things we can change are this term, and that term. So yeah, this is a very important question, and I think we can learn a lot from it. So, I mean, I kind of already answered this, but let's read it. A second spacecraft of mass 2m is placed in a circular orbit with the same radius r, And now it's asking what's going on with the period. Is it this greater than, equal to, or less than? So, as I just said, the answer is equal to. And why is that? T is equal to the square root of 4 pi squared r squared all over r cubed all over gm, right? Something like that. That's our equation for period. And the equation for period, the equation does not depend on the mass of the satellite. Mass of the satellite. It's just not in the equation. I guess I shouldn't be using the word satellite. Not only can I not spell it correctly, but it's asking about a spacecraft. But yeah, our equation for period just doesn't depend on it. So it's not going to change. It's going to stay equal. So now 4D is asking if the spacecraft moved into a new circular orbit that has radius greater than r, what's going on with the speed? Okay, this is an interesting question. Let's just scroll back a little bit, and let's use this equation here. And I'm choosing this equation because there's still a velocity term in it, and in the next step we made that substitution to account for period. So I'm just gonna copy this so we can reference it. Right, so this is the equation we were working with. Let's just simplify it down a little bit. We can see that v squared is equal to g times ms times m over r squared times r over ms. That's just multiplying by the reciprocal. That cancels with that. That cancels with that. We get v is equal to g times m over r. Square root of that. Okay, so now originally the velocity is that g times m over some r naught, square root of that. But then the spacecraft goes into a new orbit, which is greater than r. So v new is equal to g times m over r naught greater than, though. So this term in the denominator, being a little sloppy here, that has become greater than the term here. The other two terms, g stays the same, it's a constant, m stays the same, it's the same spacecraft, but here we're dividing by a term that's greater than the term here. So when you divide by a larger number, your quotient becomes smaller. So this gm over r naught greater than is going to be smaller than this term here. And then taking the square root of that, well, this would mean that this v new is less than v naught. So the answer is less than. All right, moving onwards. It is time. We always hear jokes. Oh, in physics we find the mass of the sun, or oh, what's the mass of the sun? Let's actually find it. And we're going to use some real data for this. But again, need to hydrate. Haven't been drinking much water. Okay. So the mass of the Earth is 6 times 10 to the 24. A couple of problems ago, at the beginning, I think I said it was 5.98 times 10 to the 24 kilos. We'll just round it just to keep our lives easier. But to make our lives slightly harder, we'll say that 1 year is 365.24 days. This is actually true because that's what causes leap years. If you do 4 of these, multiply this number by 4, you have 4 times 365 plus 4 times 0.24, which is nearly 1. So that adds the extra February 29th. know a couple of people that were born on February 29th. In fact, it's interesting. We're talking about the mass of the sun and like all of this astronomy stuff. My astronomy teacher was actually born on February 29th, so shout out to him. Anyways, let's continue reading. We're going to assume that the Earth maintains a constant radius of this number meters away from the sun. So that's just saying that the Earth follows a circular orbit around the sun, and it's constant, and that. Before we find the mass of the sun, let's first find the gravitational force between the sun and Earth. So, it's my time to shine. I'm going to do a little drawing here. We get a nice little sun going. One of those thingies. Got to draw a little Earth here. It's a little blue blob, and we'll give it some land, I think, that's colored green. But really, it's mostly blue. Okay, that's enough of that. And what happens is that it follows a circular orbit, right? Something like that. Make it a little less circular. Yeah, I think that's a pretty good drawing. And it's at some distance r away, so we have the value for r, but I'll just let it be capital R because we know that in our formulas we use that capital R a lot. But first, let's just write down the variables that we're given. So we're given mass of the Earth is equal to 6 times 10 to the 24 kilograms. We're given that it orbits the sun in 1 year. So that is actually the period, the time it takes for orbit, 365.24 days. Okay? And then finally we're given r equals 1.5 times 10 to the 11 meters. So part A is asking us to find the gravitational force. Okay. So we have what do we have? We have the Earth, we have the sun, so there is some sort of forces going on here. So, what is going on? We need to find this Fg. And Fg equals mg, well, yeah, we're kind of working with the Earth, but the two objects in question are the Earth and the sun, so that mg doesn't apply. If the two objects were Earth and some object on Earth or close to Earth, then we could use it, but since the sun is not close to Earth, we can't use it. So we would like to use Fg is equal to g times mass of the Earth times mass of the sun over r squared. Unfortunately, we don't have this mass of the sun term. That's something we're going to find soon, but we don't have that. So what can we do instead? Well, we have a circle. We have a force pointing inwards. That should be prompting us to think centripetal motion. So F sub c equals mac. We've been seeing this a lot today, so hopefully you're starting to think gravitation, centripetal motion, those things should be going hand in hand. And our force is F sub g, and we can substitute v squared over r for a sub c, since we don't have a sub c. So we still want to find Fg. First, let's look what is m. M should be m sub e, because that's the object doing the orbiting. R we don't have v squared. But we can get v squared, because we know v is equal to 2 pi r over t. And we have t. T is equal to 365.24 days. Unfortunately, v, the units for v are meters per second. The numerator, 2 pi r is measured in meters. The denominator, to make the units of v be meters per second, this should be in seconds. So we have to convert t to seconds. So let's just do a little bit of dimensional analysis here. In one day, there are 24 hours, give or take. In 1 hour, there are 60 minutes. And in 1 minute, there is 60 seconds. So if we do this, t is equal to approximately 3.15 times 10 to the 7 seconds. Okay, now we can solve for v. 2 pi, whoops, that is a bad pi. R, what is R? That is this quantity here, which we specified, 1.5 times 10 to the 11. And now we have t is 3.15 times 10 to the 7. This is in meters, this is in seconds. So when we do that division, we get 29,919.93 meters per second. We are traveling super fast on Earth. Nearly 30,000 meters per second. Isn't that, it's just so crazy to think about because we don't feel it. But yeah, we're traveling super duper fast. Okay, so we solve for v, we're trying to solve for f sub g. So now we have all of these quantities, so let's just solve for it. The mass of the Earth we're given is 6 times 10 to the 24 kilograms. Velocity we just solved for, which is a very large quantity, but now we're squaring it. And the radius, again, it's the same value we just used, 3.15 times 10 to the 7. And we see that the force of gravity is 3.58 times 10 to the 22 newtons. That is the gravitational force. And, I said earlier about how, when we deal with things away from Earth, other planets, they're far away. It still holds true. This just happens to be a little different. We get a large force because the sun is pretty close to Earth. So that is part A. I'm going to add a page, and then we can do part B. So part B is asking, what is the mass of the sun? And to do that, we can take advantage of what we were talking about earlier, using the other equation over r squared. Because here, we didn't know what the mass of the sun is, but now we know what f sub g is, we know what capital G is, we know what the mass of the Earth is, and we know what r squared is. So this just requires a little bit of rearranging and solving for m sub s. So we can get that f sub g times r squared, over m sub e times g is equal to m sub s. Yeah. So we can just plug this in. M sub s is equal to f sub g we just solved for. This is 3.58 times 10 to the 22 times r squared, 1.5 times 10 to the 11. I think it's supposed to be 3.15 times 10 to the 11. Let me just check. Yeah. Wait. Did I make some sort of mistake? Oh, I just made a mistake here. Yeah. This term is incorrect. I put the period there. That was the time period. This is supposed to be 1.5 times 10 to the 11. But this calculation here still holds true. So that is my bad. So this is also 1.5 times 10 to the 11. We're squaring that all over mass of the Earth, which is 6 times 10 to the 24. And then G is 6.67 times 10 to the negative 11. We do this, we get 2.01 times 10 to the 30 kilograms. And that is the mass of the sun. So now you can tell all of your friends that I know how to calculate the mass of the sun. Cool. So what did we learn from this? We learned a couple of things. Most importantly, be careful with your arithmetic. It's super easy to make mistakes, as we've seen. So just make sure you're double checking your work as much as possible. But also, before we move on, let's just take a look at this. So according to Google, m sub s, the real mass of the sun, is 1.989 times 10 to the 30 kilograms. So first of all, we were very, very close. We were off by just about 2 times 10 to the 28. Something like that, which in fairness is many, many kilograms. But you can see that our numbers are pretty close, right? So it's a good exercise to think, what is the cause for error? Cause for error. And, well, there are many, many possible things that could cause for this error, but there are two main things that we can think about that cause the error. First is intermediate rounding. We made some rounding things here and there, like here we rounded to seconds. Actually, I don't know if this is rounded much, if at all, but perhaps there was just some intermediate rounding that we did that caused the number to just go up or down by a slight amount, but that's a cause for error. But perhaps the larger cause for error is that we assumed circular orbit. Right? In the problem, we said that we assume that Earth maintains a constant radius of that much away from the sun, which meant that it traveled in a circular path. This isn't actually true. The Earth does not travel in a circular path around the sun. It travels in an elliptical path. So because of that, not all of our calculations hold true. The Earth isn't always a constant distance away from the sun. And in fact, sometimes the rocket scientists, people at NASA, take advantage of the fact of Earth's elliptical path and even other planets' path, and they can do calculations of when two objects will be closest to each other or furthest away, so they know when to schedule their missions, so that way the flight of the spacecraft or whatever, it doesn't have to travel as much distance, which is pretty cool. But yeah, that's an important factor to consider here, that we just assumed it was a circle, but in reality it's an ellipse, and that changes a lot of the things. It also changes the velocity. So here we said that the velocity of the Earth is this nearly 30,000 meters per second, but Earth's velocity actually changes along its elliptical path. It gets faster near the ends of the ellipse and a little slower in the middle part of the ellipse. This stuff all comes from Kepler and his laws of planetary motion, but it's actually really interesting to think about. You don't necessarily need to know that for this class or the AP exam, but it's still a handful information for the future. So yeah, congratulations, you have determined the mass of the sun, which is a very big accomplishment. Let's move on to our final question of the day. And again, we're looking at stars, so it's a very intergalactic theme this week, but that's just what happens when we talk about gravitation. We have two stars, A and B, circular orbits of radii r sub A and r sub B respectively. They're shown in the diagram, and they do those orbits about this point P. And interestingly, each of the star has the same period of revolution t. Pretty cool. Determine expressions for the following three quantities in terms of those constants and other fundamental constants First, we want to find the centripetal acceleration of star A. Okay, so centripetal acceleration, let's just start thinking about it. That might have something to do with this equation here, F sub c equals mac. Right, we have m. Do we have m? Can we express it in terms of m? I guess not. But that's okay. This is like the first formula you should be thinking about. And yeah, well, you're like, okay, we don't have m, so maybe that's not the right formula. So what's another formula we know? A sub c is equal to v squared over r. That's a, critical formula that we've been using a lot. We've been making those substitutions. And, well, maybe we can find this. R should be somewhat simple to find. And v, we can use the fact that that is equal to 2 pi r over t. And we have t. So this seems really promising. So let's make this substitution and then simplify for a sub c. So we get this is equal to 1 over r times 2 pi r over t squared. That's 1 over r times 4 pi squared r squared over t squared. So that's equal to 4 pi squared r over t squared. Okay, now we just have to consider what is the r that we're dealing with. And, well, we're looking at star A only. So this is the circular path. So that r, if we remember from back here, where is my note about it? Yes. In centripetal motion, where AC equals v squared over r, the r is the radius of the circular path. So if we go back to here, that is telling us our r is the radius of this circular path, which is r sub a. You may be tempted to do something with RA and RB, but for this problem, we actually don't care about what's going on with B. We only care about A. So the R should be equal to R sub A, and this is equal to 4 pi squared times R sub A, all of this over T squared. That's in terms of the constants, so that's our answer for part A. Now we wish to find the mass mb of star B. Okay, so how are we going to do that? Well, if we think about this equation here, the issue was that we didn't know the mass. But now we can solve for mass because we can do something with summing the centripetal forces, and we can calculate centripetal acceleration using some formula like that. So maybe this is the formula we should be searching for. But first, let's think about the centripetal acceleration. So we have two objects here, so there must be some force between them. And in fact, they point like this. Now the key thing about this might take quite a bit of explanation, but each star has the same period of revolution t. Okay. So what this means is we're just going to assume that they travel in constant velocities. This means that they sweep out the same angle in the same amount of time. I guess it's not very well specified here, but we're going to say that the velocities go in opposite directions. So the point about their period, that they're equal, says that if A goes to some point here, right, it swept out this area in some time, or rather that angle in some time, then B has swept out the same angle in the same amount of time. So now we have the forces pointing like that at some other point. So what is going on? You can sort of imagine this like rod here, and the rod is sort of just being turned around at these like different points in time. Something like this. Right? That's sort of what's going on here. So the stars are always opposite each other, and they're at a distance, RA plus RB. Okay, so that is key. And it's important because, well, okay, this is some sort of FG. We know that FG is equal to G times MA times MB over R squared, right? And now we can say that I know what that R squared is. That is equal to RA plus RB. That quantity is squared. Okay, so that is the gravitational force experienced by both both star A and star B. Okay, so what can we do from here? Well, let's go back to our equation that we had. Sum of the forces centripetally equals MAC. So now we have FG equals MAC. Right, because the force is pointing inwards for A, and I mean it's also pointing inwards for B, but let's just take a look at A and see what happens. If things go wrong, then we can just switch to B. What are we trying to solve for? The mass of star B. So, yeah, this is mass of A, something like that. Okay, so we just solve for F sub G, and we have A sub C for MA from the previous part. So we can start to solve for something. But first, let's make the substitutions. So F sub G is equal to, as we just solved for, G times MA times MB over RA plus RB squared. This is equal to M sub A times, from the previous part, 4 pi squared times R sub A over T squared. And of course, if we were looking at star B, then this would be M sub B, this would be R sub B, and I believe everything else would remain the same. But we can start to see what's going on here. These MAs will eventually cancel, and we'll be left with that MB, which is what we're solving for. So let us multiply both sides by the reciprocal of that. So we get MB is equal to MA times 4 pi squared times R sub A all over T squared times RA plus RB squared over G times MA times MB. Okay, and now we can do some cancellations. This MA cancels with that MA. Does anything else cancel? Oh wait, this MB here is not supposed to be there. Does anything else cancel? The answer to that is no, so that's not very exciting. We should get that MB is equal to 4 pi squared times RA times RA plus RB quantity squared. All of this over GT squared. That is the mass of star B. Pretty crazy expression right there. And it depends on a ton of things. It depends on the distance between the two stars, which is always RA plus RB. We just explained that. So that's the distance between the two stars. It also depends on the radius of the circular path that the other star takes. The mass of B depends on the path of another star, the radius of that path. What is going on here? Why would that even matter? Oh my gosh, it's absolutely crazy to think about. So that term is just completely bonkers. 4 pi squared is still around there, and then it depends on the period. In this case, the period of A. Well, it's the same period for both of them, so I guess that t term makes sense to be there. But wow, that term RA by itself, strange. Okay, so now we want to find the mass of star A. This is a very similar thing. Let's just use pink here. So we'll sum the forces again, but now let's say that this is equal to mb times AC. And we'll get Fg is equal to mb times AC. And let's just switch back to red here just to see what carries over. Fg is the same because it's the same force for both of the stars. This is equal to mb now. And then for A sub c, this term, you can do the calculations by yourself, but you'll see that it's going to be equal to the 4 pi squared term stays the same. This changes to r sub b, and then the period is the same because it's the same period for both stars. So the only thing that really changes there is it goes to r sub b, and then we do a similar thing where we multiply by the reciprocal, and we'll get that m sub a is equal to something very similar, 4 pi squared times rb times ra plus rb quantity squared over gt squared. So I'll leave this part C as an exercise for you to check. I sort of just, condensed a lot of the math into 1 or 2 steps, but it would be good for you to spend some time to check that to see whether or not I'm correct in my calculations. But yeah, that is that. And that is actually the last question of the day. So we got through a handful of questions there. Okay, so let's just exit that scene. Recap, what did we learn today? If I learned anything, it's that I need to be more careful with my arithmetic because it's super easy to make mistakes. But something that you should always remember when doing gravitation is that when we're working with things that aren't close to Earth, there still is a force between those two objects. Any pair of objects. If we have 3 objects, there's forces between all of those objects pairwise. And we now learned a formula for that force. Capital G times m1 times m2 over r squared. That formula is going to be super, super powerful. And using that formula, we were able to derive lowercase g equals 9.8 meters per second squared. I encourage you to, on your own time, try to find lowercase g for some other planet. Perhaps even for the moon. Get some data from the internet. You need the mass of whatever thing you're working on, the mass of the moon and the radius of the moon. Do a similar thing to what we did, and then check your answer to see if it checks out. And hopefully it does. We also learned a lot of qualitative assessments. So think back to the first and second multiple choice question where we had 2 scenarios. An object on a planet, and then we increased its radius, and we said, when we do that, the weight decreases. Or, when we do that, the velocity of the satellite decreases. Maybe if we made the radius smaller, the velocity would increase. Something to think about. And then we did a lot of practice about establishing relationships between these variables. A lot of these questions ask for what is the period in terms of the other variables. So I encourage you to rewind, do some of those problems again for yourself, and then do what I was doing, where I asked questions. What happens if I increase the radius here? Does the period change? Or what happens if I increase mass? These types of questions that you ask yourself, these qualitative assessments, are really going to help you out in the long run. Particularly for the AP exam, I'm sure there's going to be a ton of multiple choice questions where it's what happens to the period if you increase the mass of the object? So it's very good practice to do that. And yeah, so that'll wrap it up for today. Hopefully you learned something new. I know I certainly did. This is one of my favorite topics when it comes to physics because I really like astronomy. So hopefully you found this enjoyable too. And that'll do it for this week. As always, I'll be back on Wednesday for some calculus content, which I'm looking forward to. Thursday will be Physics C. And if not, then I will see you again next week. So until then, take care.